Here in this video, we're going to look at a non-parametric alternative to the two-sample t-test. So this would be when we've got two separate groups that are independent that we are trying to compare using a numerical variable. The test that we're going to see is called the Mann Whitney U-test. It is equivalent to another test, which is called the Wilcoxon-Rank sum test. They give exactly the same results, but they get there a slightly different way. Usually people talk about the Mann Whitney U-test instead of the Wilcoxon-Rank sum test. I think mostly because we already saw the Wilcoxon signed rank test and it's confusing to distinguish between the different Wilcoxon tests. But in R, we will use the Wilcoxon-Rank sum test, and so that's why I mention it. Recall that the conditions to use a t-distribution to make inference about a difference in means are: we need to have independence between the observations. We need to have independence between the groups. Otherwise, if we didn't, we should be using something that accounts for the paired nature of the data. And we need to have nearly normal distribution in each group, and that can be relaxed if we've got large sample sizes. So again, the question becomes, what can we do if the sample sizes are small and not both distributions are nearly normal? The Mann Whitney U-test is going to give us an answer to that question. The way that the Mann Whitney U-test works is that we state our hypotheses, which are that a median from the first group is equal to the median from the second group versus the alternative that the medians are not equal. It is possible to do these as a one-sided test also, but I'm going to talk about it more generally this way. And the example that we're going to use is we've got a company testing two proposed versions of a plane to determine whether they are equally fast. Each model was flown on a test route at 6 randomly selected departure times. The time to complete the first test flight was recorded in minutes, and because the selected departure times were not the same selected departure times for the different models of planes, the data are not paired here. The times for Model A are listed here, and the times for Model B. So there's our data. So the way that the Mann Whitney test works is this. We start by combining the data from both groups and then ranking the values from smallest to largest. Then we calculate the sum of the ranks for each group and define R sub 1 to be the larger of the two sums. We define N sub 1 to be the smaller sample size and N sub 2 to be the larger sample size. And then we calculate this U statistic. And then we use a table to decide whether we can reject the null hypothesis or not, and make an appropriate conclusion in context. So again, here's the data for our example. And we're going to start by combining the data and ranking it from smallest to largest. So here are all of the data values over here in the left column. In the right column, I've got something that is reminding me which group each of those data values is associated with, and I ranked them from smallest to largest in the middle. Now we find the sum of the ranks in each group. For Model A, the sum of the ranks was 52. For Model B, the sum of the ranks was 26. R1 is the larger of the two sums, so R1 is equal to 52. Now I'm going to calculate this test statistic. N1 and N2, remember N1 is the smaller of the two sample sizes, N2 is the larger of the two sample sizes. In this case, both samples are size 6, so N1 equals N2 equals 6. We saw in our last slide that R sub 1 is equal to 52. That was the larger of the sum of the ranks. And so when I go through and I calculate my U, I get a U equal to 5. Next, I use the table to find my p-value. I've got my N2 equal to 6 as the top, so these tables vary depending on the book that you look at. This one's giving me, first I'm choosing the appropriate table is the one with N2 equals 6. N1 here is also equal to 6. So I'm going to go down the column until I find my U in the table, which is at 5. And then this is giving me the one-tailed p-value. So the one-tailed p-value is in the table. If I want a two-tailed test, I take that p-value in the table and multiply by 2. So since I was doing a two-tailed test, my p-value is 2 times 0.021, which gives me 0.042. Now we're going to make an appropriate conclusion. Remember that our null hypothesis was that the median time to complete the test route was the same for both model A and model B. Our p-value that we found was less than 0.05. This means at the 5% level of significance, we can reject the null hypothesis, and we find that model B is faster on the test route than model A. Now, how do I know that model B was faster? I can go back and look at my original data, or I can look at the sum of the ranks. Remember, the sum of the ranks for model B was 26. That means that the times were typically smaller compared to for model A, where the sum of the ranks was larger. When we want to implement this in R, as I mentioned earlier in the video, we use the Wilcox.test function that we used earlier for the signed rank test, but we're going to specify here that paired equals false. That way it knows to do the rank sum test, which is equivalent to this Mann Whitney test, instead of trying to do the signed rank test. The other things I put in, my data are contained in the variables model A and model B. I'll tell you my alternative is two-sided, and mu equals 0 just means that I'm testing to see if there's no difference in means versus an alternative that there's some difference. And again, the Wilcoxon rank sum test comes out, and it gives us a different test statistic because the Wilcoxon gets to the p-value in a slightly different way, but it gives us the same p-value except for some rounding error associated with the table. So that is a look at the Wilcoxon rank sum test. It can be very useful in situations where you're comparing two groups and your condition of normality is not met.